estimate this function, that's one application. So the reason why we determine the equation of the tangent is because we are going to be able to approximate the function values close to 2 by using this line. So that's why we always look at the equation of the tangent line to the graph of a function at a point. This is a very important concept. Okay, perfect. Again, find the equation of the tangent line. Find the equation of the tangent line. Okay, so we can also find the first and second derivatives. Why, again, are we interested in first and second derivatives? So let me explain, and then we'll look at the problem. And how many derivatives really? And I think I'm on page 6, yes. So f prime of x is the first derivative. F double prime of x is the second. When we analyze functions, it's rare that we get to the third derivatives. But we may be asked to find. But what is the purpose? Well, these have a lot of applications. They will tell us a lot about the function. This one will tell us something about the second derivative, but beyond that, it's just an exercise, basically, in differentiation. But these three are important, especially these two. And you will see in the next chapter what they say about the function itself. Okay. So let's look at 51 and let's determine the first and the second derivatives. Also, another very important application, if this is the distance function, what will this represent? And what will this represent? So this is the rate of change of distance with respect to time. How do we call that? What is the name? A rate of change of distance with respect to time, if this is the distance. How do we call this?
It's the velocity.
Thank you very much. Velocity function, of course. Now, what is the rate of change of this function with respect to time? How do we call this one? The rate of change of
velocity.
Yeah, acceleration. If this is measured, if the distance is measured in, let's say, miles, and x is measured in hours, the distance will be measured in miles. The velocity will be measured in two measurement units, because it's a rate of change. Also, this one is a rate of change of this. So it will be miles per hours squared. So please remember the distance function has a measurement unit composed by one measurement unit, but the velocity is the rate of change, so it's miles per hour. The acceleration rate of change of this, they cannot have the same measurement unit. This is the rate of change of distance, and this is the rate of change of velocity. So we have the measurement unit for velocity divided by the measurement unit for time. So please remember these have to be three different measurement units. So to wrap up this section, please choose. You prefer to look at the acceleration, velocity, and so on and so forth, like 53. Or you prefer the first and second derivatives, the same thing, is the same concept. we're still going to look at this first and second derivatives. So which problem would you like to work on? Any preference, please?
Do 51 first, Jefferson.
Okay, of course. So let's take a look at 51. In 51, we have f of x equals 2x minus 5x to 3/4. And they want us to find the first and the second derivatives. Okay, we cannot find the second derivative before we find the first. So can anyone give us the derivative of 2x?
That's 2.
Very good. The derivative of -5, I thought my camera cut off, sorry. I didn't mean to scare you, I thought there was something changing on the screen. So, -5, x to 3/4. What do I have to write? We're differentiating this piece. So just walk me through, what are you doing so we can make sure that it's clear.
Is that negative 15 over 4?
So we have -15/4 because we have to bring down 3/4. So -5/1 times 3/4 would be -15/4. And times x. But something happens to its power. From 3/4, we have to
Take away 1.
subtract 1. 3/4 minus 1 has to be -1/4. Right. So the power is -1/4. Yes, you can bring it down, but it's better to keep it that way because we want to find the second derivative. So now let's look at the second derivative. The derivative of 2. The rate of change of 2.
Is that 0?
Exactly. So -15/4. I have to bring down -1/4. And I have to subtract 1 from the power. So -1/4 minus 1. 4 minus 1. So -5/4. I have to multiply these two. So I get 15 divided by 16, x to -5/4. And this is final. Any questions, please, on this problem? Any questions? Any questions here? Any of these? Okay. So we said we still want to look at the other one. Anyone? Do we still want to look at the other one?
Yes, please.
Okay, perfect. 53. And we have s of t equals t to the third minus 3t. And we're talking about meters and seconds. So meters and seconds, fine. Find the velocity and acceleration as functions of t. So in part A, can anyone give us v of t and a of t? So let's determine v of t first. Can anyone try v of t?
That's 3t squared
Yes?
minus 3.
That's it. Can anyone try the acceleration? So if this is in meters, this will be in meters per second, and this will be in meters per second squared. Can anyone differentiate this for us? And that will be the acceleration.
60.
60, indeed. So let's see what they want in part B. Part B, the acceleration after 2 seconds and the acceleration when the velocity is 0. So we'll see. So the acceleration after 2 seconds is a of t, and it has to be in meters per second squared. Can anyone tell us what is a of 2?
The 12 meters per second squared.
So 6 times 2, 12 meters per second squared. Now in part C, they want us to find the acceleration. Find the acceleration when the velocity is 0. Okay, so I have to first set the velocity equal to 0, which means 3t squared minus 3 equals 0. How do I solve this? Very easy. First of all, simplify by 3. So I have t squared minus 1 equals 0 equals 1. But remember, this equation has 2 solutions. But since time cannot be negative, I will say only t equals 1 second. So we are asked to find the acceleration at 1. Can anyone give us the acceleration at 1? In meters per second squared.
That's 12 meters per second squared.
So it's a of 1. 6 times 1.
Oh, 6, sorry.
No worries. Good. That's it. I wanted to discuss one more little thing here, and then we'll continue. I want to look at a piecewise defined function. Like, for example, this one. We're given a piecewise defined function. So like f of x equals x squared plus 1 for x less than 1, and x plus 1 for x greater than or equal to 1. Is f differentiable at 1? And sketch the graph. So we'll do that. So first of all, these two functions are continuous everywhere because they're polynomial. Is it continuous at x equals 1? I don't know. If it's not continuous at 1, I will say it's not differentiable and I'm done. Anyone reminds us, if you'd like, this is what I please ask you to always keep in the back of your mind. This is what we started in chapter 2, and this is continuity at the point. Very important. Since we had the test today, can anyone tell us what is continuity, the definition of continuity at a point?
The limit of f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right, which is equal to f of x.
Excellent. F of a. Yes, awesome. Good. So now, one from the left, which branch? Because I have to put it here. One from the right, which branch? Because I have to put it here.
The first and then the second.
Of course. It happens that they are in the correct order. Make sure you always verify because they may not be in the correct order. Okay, perfect. So can anyone give us this limit? And this limit, and this function value.
2.
Yes, of course. And 2, and 2. Yes,
So it's continuous.
continuous, but that doesn't
differentiable.
mean that it's differentiable. Because it may be a cusp, a corner, who knows? So now let's differentiate this. And tell me what you write. but we need to write. So I'm on page 8. So f prime of x. I'm going to write x less than 1. I'm not going to write equal to because I have not checked if it's differentiable at 1. Can anyone give us a derivative of this? And anyone the derivative of this? So I can put them here.
2x, the first one.
Is 2x. Good. And the other one?
Is it 1?
Yes. Excellent. Good. So here's what happens. The limit from the left is how much? So as x approaches 1 from the left, what is the limit? What is the limit of this when x approaches 1 from the left?
Maybe 2.
2. What is the limit from the right as x approaches 1 from the right? We all know what the limit of 1 is. How much? So what is the limit of 1 as x approaches 1 from the left?
1?
Exactly. So the limit from the left is 2, and the limit from the right is 1, which means the slope here at this point on the left is 1, is 2, and on the right is 1. So this is more steep than this one. So this definitely is a corner. We're going to graph it in a moment. So the limit from the left is 2, which means the slope on this side is 2 of the derivative. We're talking about the derivative. And the limit from the right, so the slope here is 1. So it's a corner. This is more acute than this one. This has slope 2 and this has slope 1 at this point. Although the function is continuous, but it has a corner. It will not be differentiable. So let's graph because they ask us to graph those. So let's graph those two functions. So this is f of x, and this is f prime of x. And we're going to graph them one below the other. So 1 is the key, but 0 has to be in the table. And here's 1. And remember, we have a parenthesis, and we have a bracket. Yes, it happens that they will be the same. We already determined those limits. On the left-hand side, when we plug in, so remember this uses x squared plus 1, and this uses x plus 1. For the derivative, this will be using 2x, and this you'll be using 1 for the derivative. Okay, so when I plug in 0, I get 1. When I plug in -1, I get 2. And when I plug in 2, I get 3. That's good enough. That's all I need for the function. Now for the derivative. The derivative is undefined at 1. There is nothing I can put in here. The left will be 2. The right will be 1. If you want to plug in 2, you still have 1. If you want to plug in 0, you have 0. You want to plug in -1, you get -2. So now let's graph. And you have to find a way of graphing them on the same page, one under the other. So this will be the function. And imagine that the y-axis continues. Of course it doesn't, but it has to be exactly one after the one below the other. Okay, so I'm going to graph -1, 2. I'm going to graph 0, 1. I'm going to graph 1, 1. What did I do here? Where's my function? 2. Why did I write 1?